Hey all, I'm reviewing acid-base chemistry with y'all today. We're going to start with the constants Kw, Ka, and Kb. They're all temperature dependent and they're determined by experiment, and each acid or base has its own unique value. The Ka value is what we're going to start with today, and whether an acid or a strong acid or a weak acid are known for their dissociation rates, where a strong acid would dissociate 100% and a weak acid would not dissociate 100%. You can see that in this diagram here, where a strong acid is completely separated from its protons in solution, while a weak acid is not completely separated from its formal structure. Acetic acid is commonly used weak acid in these types of questions, and you can see here in this equation how the Ka expression would be set up, where you would typically set up an icebox and want to solve for X, and use that to find the H3O plus concentration and therefore the pH. Is a common step-by-step process to follow for this type of question. Kb is the next variable we're going to look at. The strong and weak components of the base work the same as with an acid in terms of dissociation rates. Ammonia is a commonly used weak base for these questions, where we combine with water and then an icebox would be done, and then it would be plugged into the Kb expression in the same form products over reactants. And then you typically want to solve for the OH just as you solve for the H3O plus concentration to find the POH and therefore the pH. This diagram here shows you how the acid or base would react in water once it's combined. The H plus ion or the OH ion will simply separate, and the OH will drive up the pH and the H plus will drive down the pH. Kw is a constant in a constant value at a certain temperature because it's only dealing with water, and you can always derive the Ka or Kb if you know the Kw at that temperature, like at 25 degrees C, it's 1 times 10 to the negative 14th. And you can do the same for the pKa and pKb form. Buffers are a solution that resists changes in pH when acid or alkali is added to it. They typically involve a weak acid or an alkali together with one of its salts. And this is a diagram from one of our previous FRQs that related to buffers. So just to give you all that kind of thought process. Salt dissociation is another topic under this category, and it is typically the hydrolysis of a acidic or basic salt, and when it's dealing with an acidic salt, it'll typically yield pH over 7 since the OH ion is produced, and this opposite occurs when dealing with a basic salt because an H3O plus ion is produced, pushing the pH down. You can see this happening with a strong kind of effect where it levels out to 7, with NaCl being combined with water, where the partial positive charges of the H plus are combined with the Cl minus ions of the NaCl, and that creates HCl, which is a very strong acid. And then the Na plus ions are attracted to the partial negatives of the OH molecule of the O molecules, which creates NaOH in solution. And since they're both strong, it would level out to a 7 pH. The next topic is the comet ion effect, where you can see that illustrated here in this sample problem, where 0.1 molar NaCl, CaCl2, and HCl are combined. Since it's a 1-to-1 mole ratio of the Na, the Ca, and the H, you can all assume it to be all those values to be 0.1 molar. But the Cl, on the other hand, since it's present in all 4 of them and in 2 molar, in a 2-to-1 mole ratio, the molarity would actually level out to be 0.4 molar instead of the 0.1 molar due to the common ion being present in each of the 4 solutions. The next topic is the Henderson-Hasselbalch equation, which you can see here when given different values and you need to solve for another, such as the pKa or maybe for the concentration of the base. If you're given all these values, it makes it easier to solve for instead of going through the whole process of an icebox and expression and such. And there's an alternate version for the POH as well. I have an example problem here with methylamine, which is CH3NH2. It's a weak base and reacts according to the equation above, which is actually down here. And it's a ionization constant, Kb, is 5.25 times 10 to the negative 4, which shows you it's a mildly strong base, not incredibly strong. And then it's asking us to calculate the hydroxide ion concentration in the first part of a 0.225 molar solution of it. And you solve for the first part by creating by doing an icebox, of course, and then setting the concentration of each, setting up the expression here, as shown, where the OH concentration and the methylamine concentration are on top, and then the methylammonium nitrate are on the bottom, and set that equal to the Kb value. And then once an icebox is performed, you can plug those values into your expression and then neglect X, which does work out to be less than 5% error eventually, and you can work it out therefore and set it X squared over 0.225, which is easier to work with, and then square root of 5.25 times 10 to the negative 4 times 0.225, and that would give you an OH concentration of 1.09 times 10 to the negative 2. And then without neglecting X, it would be 1.06 times 10 to the negative 2, which would be your answer there. Either of these are acceptable on the AP exam. And then it asks for us to calculate the pH of a solution made by adding a 0.01 mole of solid methylammonium nitrate to 120 milliliters of a 0.225 molar solution of methylamine, assuming that no volume change occurs. And then this is the solution that would be that we could use solving with the Henderson-Hasselbalch equation instead of the traditional icebox method. You could set plug all the values. You could set pH equal to pKa, and then that equals the log of the base and stuff, and then manipulate equations around. And then the pKa is going to be 10.7, and do pH equals 10.7 plus the log of the concentration of the base over the concentration of the acid, giving you a pH of 11.15, making it a mildly strong base. And you can use the POH form as well. It just has to subtract from 14 to give you the actual pH value that they're looking for. And then part C asks for how many moles of either NaOH or HCl should be added to the solution in B to produce a solution that has a pH of 11, so that no volume change occurs. The HCl must be added because the pH has to be lowered, and HCl is a more acidic compound, which will make it do that such behavior. So, and you can do this by simply plugging it back into the Henderson-Hasselbalch equation, except using 11 as the accepted pH instead of 11.15, and then use 10.72, the same pKa, and then log of the concentration of the base over the concentration of the acid. And then you can find out the log of the base over the acid equals 0.28, and then therefore you can plug it back into an equation and through the expression that you had earlier to find that it would need to be 0.0227 molar as the concentration of the acid, and then divide that by the 0.12 liters that you were given, and then you would need 2.73 times 10 to the negative third moles of HCl to get the pH to drop to that 11 mark. And then finally, a volume of 100 milliliters of distilled water is added to the solution in C. How is the pH affected? This ratio does not change in the buffer solution with dilution. Therefore, no effect on the pH whatsoever. Thanks for listening. I hope this review will be all well.